So this video is going to talk about the heat transfer library, and specifically about the boiling and condensation part of the heat transfer library. So if you open up EES and you go to function information, as I'm doing here, and then you go to heat transfer and fluid flow, you can see that one of the selections here is boiling and condensation. And if you select boiling and condensation, down here you've got a few options. There's functions related to pool boiling, flow boiling, condensation, and pressure drop. We're going to focus on the pool boiling condensation. The pool boiling part of the library here. So this is functions and procedures that will help you predict the pool boiling curve, right? So I'm going to look at the different functions and procedures here. You can scroll through them if you want to see them all at once. You select this information and it'll get this help menu. And let's go to the index, and you can see there's, I think, 10 different functions here. And we need to understand how these functions relate to the boiling curve. And then what we'll do is use them to actually generate a complete boiling curve that's flexible in terms of the fluid or whatever you want to change here. So let's go look at the boiling curve. So this is a generic boiling curve. You can see it consists of different regions, right? So these boiling curves are usually the applied heat flux as a function of the excess temperature difference. So for saturated pool boiling, that would be the temperature less the saturation temperature. And so down here at very low excess temperature difference and very low heat flux, so this lower left corner, you don't have any boiling at all. Actually, here you've got free convection. And then at some point you start nucleate boiling. So that's this point right here, onset of nucleate boiling. And at that point, you can see the applied heat flux goes up faster than the excess temperature does, even on this log scale. And the nucleate boiling persists until finally you hit critical heat flux. If you're running this experiment in a applied heat flux controlled manner, which is the typical way of doing it, then at that point you get what's called burnout, or the boiling crisis, and your excess temperature difference skyrockets over to here where you hit the film boiling curve. So film boiling here is where you are completely blanketed by a low conductivity vapor, whereas nucleate boiling is where you have liquid that comes into contact with your surface. So that gets you all the way over to here, and further heating would push you up the film boiling curve. If you cooled, you see the hysteresis in the boiling curve, where you're cooling now and you remain in film boiling even below the critical heat flux. And that persists all the way down here to the minimum film boiling temperature, or the Leidenfrost point, at which point you spring back over, so the excess temperature difference drops a lot until you get back onto the nucleate boiling curve. And then if you keep cooling, you do some nucleate boiling and then some free convection. So this is the boiling curve, and we would like to generate the boiling curve using these different functions. So if you look at the functions, you can see that they each pertain to different parts of the boiling curve. So these four functions at the top, these are all the nucleate boiling curve. They're different correlations, but they're supposed to represent this part of the curve here, from the onset of nucleate boiling to the critical heat flux. Then you have two functions here that just predict the critical heat flux for you. And you've got three functions that predict the film boiling part of the curve here. And then finally one function that predicts here the minimum film boiling temperature, so the Leidenfrost point. And of course there's other convection functions, natural convection functions, that could predict free convection heat flux. So we have all the pieces then to build the boiling curve, and that's what we're going to do in this video, is build a boiling curve using EES. So if you think about doing this, we need some kind of a strategy, and the sort of complicated bit here is we have to know, where do you stop being free convection and start being nucleate boiling. And then, so that's point A. And then once you climb the nucleate boiling curve, where does that stop? So that's a critical heat flux, that's point B. And then where does that critical heat flux intersect with the film boiling curve? That's point C. And then of course you need to know the bottom of the film boiling curve, that's point D. And finally, if you snap back to the nucleate boiling, curve, where on the nucleate boiling curve do you intersect with the heat flux at this Leidenfrost point, and that's point E. So the way we're going to build this boiling curve in EES is the first thing we're going to do is write 5 sub-programs so that we can actually solve equations versus use assignments that give me points A, B, C, D, and E. And once I have those points, then it's very easy to write an array that just fills in the line from 0, 0 to point A using free convection, and point A to point B using nucleate boiling, and point B to point C. That's easy. That's not even any correlation. It's just horizontally moving. And then from point D to some heat flux way above C to get the film boiling curve, and then finally D back to E. And once I have those that information in an array, I can just make a plot and set the auto update feature to the plot so that if I change something, so for example change from water to isobutane to some other fluid, the plot will just adjust itself, and I'll have then an auto-updated version of my boiling curve. Alright, so let's go ahead and set the unit system first. So here I'm going to do $unit system, SI, mass, what else, Kelvin, Pascal, joules. So I need to set the unit system because I'm going to call a whole bunch of functions that themselves call properties. I also need to set the fluid, so maybe we'll use water. The pressure is, I don't know, let's do 10 atmospheres. Of course I have to convert that to Pascal. We're going to do this for a cylinder. So the diameter of the cylinder will be 3 millimeters, which I need to convert to meters. What else? I also need the emissivity eventually for the film boiling correlation, so we'll set that to 0.7. And then finally I'm going to need TSAT for most of these functions. So TSAT, I'll use the TSAT function with $, and P equals P. So let's go ahead and solve that. And that all looks fine. So now we'll go ahead and find point A. And if you recall, point A is where the nucleate boiling curve intersects the free convection curve, right? So that's going to be an iterative solution to find that. So I want to make sure that I'm using not a procedure or a function, but a subprogram. So subprogram, maybe I'll call it find A. Subprograms are going to take in some inputs. So my inputs are going to be, I have to know the fluid, I got to know the diameter of the wire, I got to know the saturation temperature, and then it's going to give me back some outputs, and the outputs are going to be the coordinates of point A. So dTA, so the excess temperature, and Q dot A. And we'll put end. And the other thing I'm going to do right here is set the units of all of my variables using a $var_info command, and I'll also set the guess values for variables that are going to be iterated on. So here's $var_info. D has units of I guess meters. $var_info TSAT must have units of Kelvin. What else? $var_info DTA has units of Kelvin, and then $var_info Q.A has units of watts per meter squared. And I know that I'm going to have to iteratively change these two guys to try to figure out, where that intersection point is. So I'm going to go ahead and put a guess here as well. So guess equals, I don't know, 10 Kelvin or something, just so I start in the right spot. I might even need to go in and put a lower limit and an upper limit, but I don't want to do that unless I have to. All right, so there's my units. First thing I'm going to do is calculate the heat flux using the free convection library. So go to options, function information. We're in heat transfer. We're going to go down to convection. And there's a bunch of choices here, but I'm interested in free convection, and I'm going to use the dimensional version. And then we got to scroll over to find the cylinder right here. So here's the cylinder. So I'll call this procedure. It needs the fluid string, so that's $. TS is the surface temperature, so that's going to be TSAT plus DTA. T infinity is just Tsat. P is the pressure, which I didn't send in, so I got to get it. P is equal to Psat, F$T equals Tsat. And diameter I have, and it's going to return back H. So this is H for free convection. The Nusselt number, which I don't really want, and the Rayleigh number, which I also don't really want. So my heat flux due to free convection, Q dot FC, is just equal to HFC times dTA. And that has to be equal to the heat flux due to nucleate boiling. Go back to the heat transfer library. Now we're going to go to boiling and condensation. So there are a bunch of the nucleate boiling correlations here. You can see there's 4 different choices. I'm going to choose the Cooper correlation. I guess it doesn't matter, but I'll paste that in there. So this is Q dot nucleate boiling. And you can see I need to send the fluid, Tsat, T-wall, which is Tsat plus dTA. And then this last parameter, I think, is the roughness. And if you give it a negative number, it'll use a default value of roughness. So I need this subprogram to adjust this dTA until these two heat fluxes are equal to each other. So that's the last equation I got to enter. Q dot FC is equal to Q dot NC. And then Q dot at point A is just one of these two. So Q dot NC, not ND, NC. So hopefully that works. I'm going to go ahead and call it. So let's just copy this. And we're going to do call find A, F$D, so DTA. So that should work, I hope. Calculate solve. And there it is. So it's found that the nucleate boiling curve stops at this temperature rise and this heat flux. So it doesn't, the natural convection curve doesn't extend very far under these situations. So the next thing to do is find points B, C, D, and E on this boiling curve. And I'm not going to sit here and make you watch me do that, so I'll just write those and we can come back and look at them and see how they work. So here's the program with the other sub-programs written. So here's find B, find C, find D, and find E. And if we just compile them. So if we go through them, hopefully they make sense. Here, find B is finding the top of the nucleate boiling curve. So here you're basically finding what is the critical heat flux, right? And where the critical heat flux happens, that's going to tell you the excess temperature at the top of that curve. So that's point B. Point C here is when you have the boiling crisis and you use this critical heat flux. So whatever you found here in find B, you want to find where that heat flux puts you over on the film boiling curve. So that's what I do here is I give it the heat flux from B, and it keeps that same heat flux for point C and figures out what is the delta T at point C on the film boiling curve. And then we have point D. Point D is the bottom of the film boiling curve. So here you're going to first of all figure out what's the temperature at the bottom of the film boiling curve. And then once you have that temperature or that excess temperature, you can figure out what is the heat flux at the bottom of the film boiling curve. And then finally point E is you keep the same heat flux. So whatever you got for point D, you can see that's an input for find E. And you see where does that heat flux put you back on the nucleate boiling curve. So I'm going to use the same nucleate boiling correlation, and that gets me point E. And if I solve, I should find that I have all 5 of my points now, right? And one thing that you'll notice is, you go from here's where free convection stops, there's where you get critical heat flux. Here's where you have the boiling crisis and you flip over to film boiling, and this temperature difference rises by several orders of magnitude. And then as you come back down, it's still very high until you snap back over on the nucleate boiling curve. And if you look at the heat fluxes, they're changing by many orders of magnitude as well. So you're going to want to put this onto a log plot, a log plot, because it's just temperatures and heat fluxes are changing dramatically if you're going to include the film boiling part of the boiling curve. All right, so the last thing I want to do here, and I won't do all of this either, but I would like to generate arrays that will help me build the actual plot. So every one of these curves, right, there's a curve from, for the free convection, there's a curve for nucleate boiling, there's a curve for the boiling crisis, there's a curve for the film boiling, and then there's a curve to snap back over to nucleate boiling. So each one of those curves needs some points on it, so I'm just going to use, 31 points, and I'll put these in an array. So duplicate I equals 1 to n, end, and let's just do the nucleate boiling part of the curve. So the nucleate boiling part of the curve goes from what we call DTA, which is where free convection stops, to DTB, which is where you have critical heat flux. So DT, we'll call it nucleate boiling sub I, is going to be equal to DTA plus DTB minus DTA times I minus 1 divided by n minus 1. So this puts 31 points starting at DTA and ending at DTB. And for each one of those DT points, I need a heat flux. And of course, I'm on the nucleate boiling heat flux part of the boiling curve. So I got to call the right correlation. So we're using the Cooper curve. So I'll just use that right here. So Q dot, this should be nucleate boiling, sorry, MB, Q dot MB sub I is going to be equal to nucleate boiling F dollar Tsat, this is Tsat plus delta T MB sub I, so this is me climbing up the curve, and then minus 999. And hopefully if we solve, we'll have now an array. Let's see, I gotta set the units, but this is me moving up the nucleate boiling part of my curve. Probably since I was going to use a log plot, I should use logarithmically scaled DTs, but I'm not going to do that. So I got to go ahead and do the same thing now for the free convection part of the curve, the boiling crisis, and then the film boiling part of the curve, and then the snap back to the nucleate boiling. And then I'll have 5 sets of DT Q dot information that I can plot onto one plot to give me my boiling curve. So let me write the last little bit, and you can come back and see what that looks like. Alright, so this is the part we did sort of together. This is the nucleate boiling part of the curve. This next part is me getting the free convection part of the curve down at the sort of bottom left. And then this is moving from B to C. So this is the boiling crisis, right? You'll notice that the heat flux stays the same, but the temperature rise just increases until you hit the film boiling part of the curve. And here's the film boiling part of the curve, and it's going to go from the Leidenfrost point up above the critical heat flux. So here I went 20 times higher than Q dot C, so we can just see what that looks like. And then this last bit is snapping back over from the Leidenfrost curve back to the nucleate boiling curve. So I should have an array that has all this information in it, right? And I need to plot all these different things to make my my boiling curve. So let's go ahead and try to do that. So I'm going to plot, new plot window. I guess it doesn't matter. Let's start with the nucleate boiling part. So let's see, the excess temperature is X, and then the heat flux is Y. And I think I'm going to go ahead and set this up to be a log plot. I'm going to anticipate that this is going to need to be eventually a pretty big scale. The heat flux maybe I don't know, 0.01 to, this is not going to be big enough, but it's also going to be a log plot. Let's put some grid lines. So here's the nucleate boiling part of the curve. Maybe we want to make that a little bit thicker and red. Okay, so now let's start adding some of the other parts of the curve. So let's see, overlay onto this. I guess the free convection part of the curve might be good. So natural convection. So DTNC, and somewhere I have a Q.NC right here. And let's take away the symbols and maybe make that blue. See what that looks like. So that's way down here. Probably I should go to even lower values here. So let's see, maybe 0.1. Maybe 0.01 on the temperature scale. Alright, so there's free convection, and then here I transition to nucleate boiling, and next I need to put the boiling crisis on here. So let's overlay that. So overlay, what would this be? I think it's B to C, right? BC, and then here's BC, and we will make this green, I guess. So there's the boiling crisis, and then I need the film boiling part of the curve. So let's overlay that. So I have DT film boiling, and then there's other film boiling, and maybe we can make that some shade of green. So there's film boiling. I probably need to make this a little bigger, so maybe 10, and this needs to be bigger, so maybe 9. Yeah. And then the bottom of this needs to snap back over here, so that's the last bit. So plot, overlay plot. What did I call that now? I think it's ED. There's DTED, Q.ED, and yeah, there's my entire boiling curve. Right here's nucleate boiling. I'm sorry, free convection, nucleate boiling. This is critical heat flux. Then I'm over here on film boiling, and there's my hysteresis, and I come back over here to nucleate boiling. Some things I can do to make this nicer, I guess. One thing is probably let's use exponential with 0, so that makes this look a little better. This should be just heat flux, watts per meter squared. This should be just excess temperature in Kelvin. And yeah, that looks pretty good. I could add some labels. I think the next thing I'm going to do is duplicate this, and then I'm going to go in and make all of these auto update. So like this, and this. We're going to make them all auto update and hit OK. And the reason is because now I think I have a situation where I could go back here and change water to, I don't know, isobutane or something else, ammonia, whatever, and solve. So we solve. And if I go look at my plot, this has now adjusted itself for what the boiling curve would look like for isobutane. And you could change the pressure. You could change the emissivity, which would only change what's going on over here. But I have a sort of adaptively drawn boiling curve, which is really pretty cool.